Alright, so we're going to be looking at this roller coaster problem to understand conservation of energy. So when we look at this, it says a roller coaster ride in an amusement park lifts a car of mass of 700 kilograms to point A at a height of 90 meters above the lowest point on the track as shown above. The car starts from rest at point A, rolls with negligible friction down the incline, and follows the track around a loop of radius 20 meters. Point B, the highest point on the loop, is at a height of 50 meters above the lowest point on the track. So for part A, it says indicate on the figure the point P at which the maximum speed of the car is attained. Well, if we look at this, we know that up here we have the maximum maximum potential energy, which is mgh. So at this very top, at part A, it's going to have the most potential energy. When it reaches its lowest point, all that potential energy is going to become kinetic energy. So I can call this max 1/2 mv squared. So indicate on the figure the point P at which the maximum speed of the car is attained. So I can call this point P. And that's where it's going to be the fastest, because all that kinetic energy from the top at point A becomes kinetic energy at the very bottom. The next question asks us to calculate the value of the maximum speed. And we can paste this on here. Calculate the value of the maximum speed. Well, again, I know that the initial potential energy has to become the final kinetic energy. So this is just an example of conservation of energy. So the initial energy has to equal the final. So we have initial potential energy plus initial kinetic energy equals final potential energy plus final kinetic energy. I know that the initial kinetic energy at the very top, we're going to say starts from 0. And we can read that in the problem. The car starts from rest at point A. So, and then at the very bottom, there's no more potential energy. So I know that the initial potential energy has to equal the final kinetic energy. That's going to be mgh is equal to 1/2 mv, and that's going to be our max squared. So our masses cancel, and I have 2gh is equal to v squared. So now what I want to do is I want to square root both sides. And so plugging in our values, we have 2 times 9.81 meters per second squared times the height, which is 90 meters. And that's going to equal to V max. So we can put this into the calculator and figure out what it is. So 2 times 9.81 times 90 is going to give us a value of 42 meters per second. And that's going to be the velocity at the very bottom. Again, all we did here is set the initial potential energy at the very top equal to the final kinetic energy at the very bottom. What about the next part? So for the next part, whoa, didn't want to do that. So for the next part, I want to calculate the speed VB of the car at point B. So let's look at the picture again. So now what we're looking at is that this is the height that it travels from there to B. So this potential energy is going to become this kinetic energy right here. So it's the same as if it had just fallen that distance right there. So all we have to do is set those two equal to each other. So initial energy has to equal the final energy. And in this case, we can say that it's just the initial potential energy has to equal the final kinetic energy and the final potential energy. And we want to find VB, so this is MGH, and I can call it MGH1 for the 90. So H1 is 90 meters. H2 is 50 meters. And then this is 1/2 mv at b squared plus mgh2. Notice again that I can cancel out all the masses. And I'm going to take this part and subtract it from both sides, so minus gh2 from both sides. And so I get g h1 minus h2 is equal to vb squared over 2. So I can multiply this by 2, get g h1 minus h2 is equal to vb squared. The square root of this, 2g h1 minus h2 is equal to vb. And plugging in our numbers, we get the square root of 2 times 9.81 times 90 minus 50, which is just 40, which is essentially, from looking at the picture, as if it had just fallen 40 meters. So the picture that I'm looking at is over here. The distance right here is just 40 meters. So what I could have done is just set MGH and made at H 40 meters, and then this kinetic energy would be in the kinetic energy at B. So if you imagine the trajectory of this, it's all potential energy becomes kinetic, and then right here it becomes potential again, and some kinetic, and it loses more and more kinetic to become potential, and then some of that potential becomes kinetic again, until it reaches maximum speed again when it's level with the ground. So plugging this into my calculator, I get 28 meters per second is equal to V at point B. For the next question of part C, it asks, on the figure of the car below, draw and label vectors to represent the forces acting on the car when it is upside down at point B. Well, if we look at the picture again, at point B, it's on this loop-de-loop. And what we're looking at is centripetal motion. So it's going to have a centripetal force making it go down. So at point B, it has the normal force of this loop pushing it down, but it also has the weight pushing it down. So we have two forces. So if I was to draw that, I would have the normal force going down due to the rails, and also the weight of the car going down. So at point B, it has two forces pointing down, the weight and the normal force. So now we want to calculate the magnitude of all the forces identified in part C. Well, when we do a summation of forces, we see that if we make this y and this way x, and in this case we probably don't want to do that. X doesn't really matter, but we probably want y to be on the bottom because both our forces are going downward. So summation of forces in the y direction would just give us N plus W is equal to MAY. The question is what is going to be AY? Well, it's moving in a circle, so it's the centripetal force, so that's going to be V squared over R. And if we look back up at the picture, we know what the velocity is at that point. We calculated it was V at B. We also know the radius, it's 20 meters, tells us right there. So we can use that to figure out the different parts. So V, we figured out, is at point B, which is 28 meters per second. And we also know that R is 20 meters. So we can find out what W is, because W is always what it is. It's just mg. So the mass of the car is going to be 700 kilograms times 9.81. Meters per second squared. Plugging that into the calculator, I get 6,867 newtons. So we can say that W is equal to 6,867 newtons. The normal force from the above equation is equal to MAY minus W. And we know that AY is just V squared over R. So we have the mass, which is 700 kilograms, times the velocity, which is 28 meters per second, squared, divided by 20 meters, minus the 6,867 newtons. So N is going to equal to 700 times 28 squared, divided by 20, minus 6,867. So that is going to give me a normal force of 20,573 newtons. So we can see here that the roller coaster rail actually has to push off quite a bit to keep the roller coaster going in a circle. And that makes sense because if n were close to 0 or at 0, that would mean that there would be no normal force passing right here, and there would only be weight. So it might not have enough centripetal force to keep it in a circle, and it would just fall. So now suppose that friction is not negligible. How could the loop be modified to maintain the same speed at the top of the loop as found in part B? Justify your answer. So before, there was no friction, and now there is friction, but we want it to be going just as fast as in at part B. So we figured out what VB was. Well, since we're going to lose some energy to friction, one thing we could do is we could make the loop smaller such that it doesn't go to the same height. And there's other things that we could do, but that one would be the easiest solution, is just to make the loop smaller so it just doesn't go to the same height. So this concludes this problem. Hope this helps. Let me know in class if you need some additional help.